Right, so the first speaker is Vincent Esposito from Sadat.
Hey, good afternoon, everybody, and thank you for the opportunity to tell you about small data tools today. So I'm Vincent Esposito. I'm part of the experimental control team at LCLS, and I want to tell you about a little piece of software that we use to help our users do data analysis at LCLS. So what is small data tools? Well, as introduced this morning by Yana, LCLS Data System is a very complex piece of software and system overall. And so we want to provide the highest level of abstraction for users. And so when they come, they have an experiment. They use the data acquisition system, which records files in an XTC format, which is very nice to write to, but not so nice to read from. And so the data system team has developed the PSANA package, which is sort of the package that allows us to read those files. And on top of that, we've built small data tools, which leverages PSANA and its parallel capabilities to provide configurable pre-processing reduction of the data. The idea is to provide a file for users, which is in a more convenient format, typically HDF5, that is suited for them to explore and analyze in Jupyter notebooks. We mainly have two pathways for reduction. One is event-based reduction, where we keep all events, but try to make each of them smaller, or we bin or aggregate events together in the bin data reduction. The goal is to abstract the event loop, the calibration and the scaling, detector calibration and scaling from the users so that they can focus on their science. And this is used at most instruments at LCLS as sort of the high-level analysis package. As I was mentioning, we have two different approaches. First, we have the event-based reduction, where the idea is to keep all events but make them small. So typically, we're going to keep most of our scalar detectors. These do not contribute much to our to the data volume, but we'll try to reduce as much as possible array detectors and waveforms detectors. So we basically have a library of predefined reduction function. This goes from the simple region of interest or projection, which just crops the image, for example, to more complex algorithm like droplet and photonization, where the idea is to extract a photon count in an image. So essentially, we can attach a mini directed acyclic graph to any detectors, defining a set of functions that we want to apply to that detector. So on the bottom here, I show an example of what it would look for the droplet and photonization step, where we first dropletize our image, which means we look for connected islands of pixels above a certain thresholds. Then we sort of try to we use the greedy guess algorithm to place photons within each of these islands. And we finalize the data analysis by sparsifying the results so that we can write a reduced data to H5. This approach is generally very liked by our users because it still has, the output file still has every events so that they can easily aggregate some, bin them as they want. However, as we're moving towards very high rate data, even small amount of many events is still a lot of data. And so this is becoming even a problem for simple analysis in Jupyter notebooks, where we, to give you an order of magnitude in LCLS-I, given experimental run, we'll typically have the order of 100,000 events. And in LCLS-II, as we're ramping towards tens of kilohertz now, we have upwards 10 million events in a single run. So in general, for LCLS-II, we would prefer them to use the second features that we've coined the cube, which basically is multidimensional histograms of the data. So can you imagine for step scans, for example, you will want to just bin or average your data for each step or sum the data, but you can also do that in a customized way where any experimental variable can be used as a binned axis. This second approach is a little bit more of a black box sometimes to our users because it does apply all of the filtering and screening that users generally like to be able to tinker with in the offline data, in the offline Jupyter notebook, excuse me. So for example, we need to split laser on and laser off data already at this stage. We need to apply filters on our X-ray diagnostics, etc. And this is all things that are now done in the Slurm job, which is often a little bit more intimidating to a non-computer scientist or software developer. To give you an idea, so why we want to hide the scaling and these things from our users, well, this is kind of a snapshot of what the MPI communicator and groups look like in PSNA. Without going into the details, each of the colored box represent one group or communicator. And so obviously we cannot expect our users to be familiar and know all the knobs for the parallel processing. I mentioned here, LCLS PSNA1 was embarrassingly parallel, just round-robin events to the many codes that we use, so parallelization was fairly easy. However, in PSNA2, we had that complex layered parallelization steps, which we want to abstract from the users. At the same time, we want to retain control over each of the knobs ourselves when we deploy the job for users. The interface that users are exposed with is the ARP, that stands for the automated run processing. This is a way of where we can define predefined jobs and scripts that will automatically be run based on some predefined trigger. They can be manually run or at the start of a data run, or other trigger based on some experiment variables. So typically what we'll do for each experiment is we'll deploy the submission script for small data and users can then just either let the trigger run the jobs or submit the workflows manually using the workflow tab in the LCLS experimental e-log. Generally, this hides the complexity of scaling and submitting Slurm jobs to our users and allow them to have their pre-processed HDF5 file available within minutes after the run is over. I want to end with just a few comments about what are the challenges and that we're facing supporting our user community. We welcome a wide range of users from many different backgrounds. Some of them are experts in programming and parallel computing. Others have just heard about Python a few days before coming to the Beam time. And so using the same tool to sort of cater to those wide extremes set of skills is challenging. On one hand, we need to provide all the available knobs for the people who know how to use them, while on the other hand, we need to hide the complexity for people who are intimidated by it. I think a very complex aspect, and I'm sure you're all exposed to that, is as our systems and our data pipelines become more complex, so do our tools. And these tools often become black boxes to the end users, and our users are generally scientists who, by definition, do not like black boxes. And so it is a very challenge to sort of ensure that they still trust the output of our tools. And we strive to do that by providing as much as possible insights into the pre-processing step by providing diagnostics, plots, and visualization that give insights on how the processing is going. So typically, for example, we'll provide this type of plots which show that a given threshold that they have picked would still be valid for their analysis, right? So we try as much as possible to provide these summaries, which can be actually visible directly into the e-log of LCLS. And finally, as the type of experiments that we're doing and the science that we're after constantly evolves, we have to strive for a balance between stability and continuity and versatility of our tools. I think in small data tools, we may not always be the best at the stability, I must confess. We are constantly in almost development stage, trying to catch up with what our users want and work closely with them. And with that, I want to conclude and thank you for your attention.